Good day everyone, my name is Moe Shahram and this is course Physical Science Survey PSCI 10 at West Valley College. Today we are going to cover chapter 5 which is about the concept of wave and sound. Waves and oscillations are very important subject in physics and physical phenomena, so we are going to spend a lot of time and also a lot of animation and video demonstration for this chapter. So let's go ahead and ask ourselves, what is vibration? Well, if you have your cell phone on silence and you're holding it in your hand or in your pocket, when you receive a call, what do you feel? You feel some oscillation there, some vibration there. So vibration is a wiggle or oscillation in place, in time. You feel that vibration but don't hear anything. However, if your ringer is on, you also hear a ring. Now that ring that you hear, it's a wave that is propagated from the speaker of your cell phone into the air molecules and eventually reaches out to your ear and you hear that. Vibration is oscillation in time. A wave is oscillation in time and space. So those are the two different definitions of waves and vibration. For example, if you let your finger, you basically are oscillating in time. But if you do that over the surface of a water on a pool or some standing water, then you notice the waves that propagate as you touch surface of the water. That is the wave that is being propagated. These are some examples here. Pendulum that is going back and forth, ocean waves, earthquake waves. Because waves move in a space, the mere motion of the wave carries energy. And that energy propagates throughout the space. Now notice, if you have a cork on the pool and then you start vibrating the water with your finger, as the waves propagate, the cork goes up and down as the wave passes by the cork on the surface of the water. The cork doesn't move away, it just goes up and down. What happens, the energy is being propagated and the vibration of that cork is still up and down in pretty much the same place. Now, some waves, such as sound waves, ocean waves, they need media for it to propagate. But it turns out that electromagnetic wave does not need any media. They travel through the vacuum. Another example that the energy is propagating, not the material, not the media, is that if you have a very long piece of pipe, a steel pipe, and you bang on one side of it, you hear the sound on the other side. None of the molecules or atoms inside that pipe are moving. They're just transferring the energy of sound from one end of the pipe to the other end of the pipe. It's important to keep in mind that wave transfers energy. Another example is when earthquake happens. Earthquake happen localized in certain portion of the Earth's crust, and that motion and movement there sends out energy throughout the Earth. So it needs a media through the interior of the Earth, and it propagates throughout the entire Earth. Of course, if it is not that strong, you won't feel it anywhere else. But if it is strong, you can even register it on the other side of the Earth. And we do have instruments that they can actually make those sensitive measurements. And we'll discuss that when we talk about geology. Now, let's see what are the properties that describe a wave. In this example here, if you have a pendulum that just goes back and forth, it has a little pen at the bottom of it, and then you have a sheet of paper that you can roll. You notice that it puts a very peculiar path on the paper. This behavior is called the sine curve or sinusoidal curve. And that is the property of really the simple oscillation. We call that simple harmonic wave. A wave can be represented by a sinusoidal behavior, which is an oscillation. This graph represents oscillation of some wave in space. So we can represent that with how long does it take for this wave to repeat itself. We call that a wavelength. Now, how high that goes and how low that oscillation happens, that's called the amplitude of the wave. Now, if you have a vibration, that something vibrates in time, then you can also show that with this kind of sinusoidal behavior. But the difference is now the axis is in time, not in distance. The change is in time, not in distance. And the corresponding distance that we had is called now period, because now we are looking at the change in time. Every one cycle that happens corresponds to a period of this oscillation. It is important to distinguish between these two representations, because sometimes you're given a graph, the axis is on time, sometimes with respect to distance, and you need to kind of distinguish between the two situations. So other parameters that describe a wave would be the amplitude, as I mentioned. Now, amplitude is how high a wave oscillates from the center of oscillation and how low. This is a positive amplitude and this is a negative amplitude. So amplitude is a displacement of a wave from its equilibrium position. Period we talked about, the time takes for one cycle to complete. Wavelength is the distance it takes for one cycle to complete. And frequency, now another parameter that is useful, and we use that a lot to describe how fast a wave cycles in 1 second. So number of cycles per second is called frequency or pitch. Mean the same thing, especially in sound we call it the pitch. Now let's look at the units, because units are important. For wavelength we have meter, because it's a length, it represents a length. For amplitude we also have meter, because it represents how high or how low, that's a length. For period, obviously it represents second. For frequency, it represents how many time per second. So how many cycle per second. So it's just cycle per second. So cycle doesn't have any physical unit, it's just a number. Essentially, this is 1 over second. And 1 over second, we call that Hertz, after Mr. Hertz. And then, obviously, as you notice, the water waves in ocean, they travel. Or as you oscillate your finger on the surface of a pool, the circles travel throughout the surface of the pool. They cover a certain distance in time. So that's the velocity, distance of travel in 1 second, meter per second. And then we said anything that moves carries energy. So, well, there it is. Energy is transferred from one place to another. The ocean waves that are generated somewhere, they come and hit the shore. have a lot of energy. That is described by unit of joules, just like all the other energies that we talked about. So that's how we describe a wave. Now, the relationship between these parameters are interesting and important. So frequency is 1 cycle per second. The time it takes for 1 cycle, it's period. Frequency is 1 over period. Velocity is distance covered in time. One wavelength, which is that much, lambda, that's distance, covered in 1 period, that is the velocity. Okay, so velocity is equal to lambda over t. So you just can use this and combine it with the above equation, because f is 1 over t and v is lambda over t. So if you want to know what is the relationship between the frequency and velocity, then you just plug that in this equation and you get this interesting equation, which is tells you velocity is equal to lambda times f. So all we did was we said, because we know f is equal to 1 over t, so t is equal to 1 over f. We can rewrite that, right? And then we put that in here, and velocity would be lambda over 1 over f, which denominator goes up, and then you have lambda times f. So these are the relationship that describes a wave. Now we talk about what different types of waves we have. Well, we have 2 types. One type is called longitudinal wave, that as the wave oscillates, the oscillation is in the same direction along the line of propagation. I have an example here. You have this spring, and then you just oscillate this back and forth on one end, and you notice that oscillation propagates along the line of the wave velocity. That's called longitudinal wave. Now, if you take the same spring and oscillate it up and down, you see that oscillation propagating, but it's always up and down with respect to motion of the wave. So it's perpendicular to the motion of the wave. So those are the 2 different types of waves, and each one have their own characteristics we will talk about. So let's look at just longitudinal wave. Notice that in that media, in this case this media is this spring, just oscillate in place. However, the wave propagates throughout the media. The areas that are compressed are called compression, when the areas are kind of oscillating in a compression form. And then when the areas are kind of stretched and oscillate, that's called rarefaction. A very important example of longitudinal wave is a sound wave. Sound wave propagates throughout many different types of media. Through air, molecules of air are being oscillated by the vocal cord of my voice and then propagates throughout the space. They propagate in metals, steels, solids, and also in liquid. Earthquake propagates through the molten portion of the earth, through the crust, through the interior part of the earth, specifically the P wave, which is the longitudinal. Then we have transverse wave. Let me see if I can show you an animation here. So this is a spring with some mass hanging on it, and it's oscillating. So it's basically a simple oscillation. We call that simple harmonic motion. And if you have many of these that are oscillating at a different time, then you would have an oscillation which we call it a transverse wave. Because now, as you can see, the oscillation is perpendicular to the propagation of the wave. And you can see the wave is propagating. In this example, you see that we have molecules of air that are oscillating back and forth in place. Now, pay attention to one of these particles of air, molecules of air in this pipe. This is, example of sound wave. As the sound wave travels, these molecules, basically all of them, oscillate back and forth. However, you notice that the energy of these waves is being transferred and moved from left to right. So the wave is propagating through the space. However, each particle, as you can see, it just goes back and forth. When you look at the transverse wave, you will see that the wave is oscillating and propagating in space. However, the oscillation of each element or each part of this media, it's up and down. And that is in this animation, and that shows that this is a transverse wave, just like the ocean wave. Look at the ocean wave. If you notice, one particle goes through some sort of a circular or elliptic motion, but it just stays in place. But the wave is propagating, as you can see. These are some of the animations and links to these animations. So if you want to go back and look at them, you can do that. Here's another one. Suppose you have a string. You can have a piece of rope, okay, and you start oscillating that. So what happens? When you do that, waves are generated and waves are propagating, and it's going through the media string. So you can change the amplitude of this, or you can change the frequency. Now later on we'll talk about what happens if you have a fixed end, and we will see the interesting phenomena there. What happens if you have some sort of a damping? The waves damp out and stop oscillating. Eventually they die out. So we'll look at some of these examples later on. We have different types of waves. The simplest and very interesting one is the sine or cosine. We call it sinusoidal. You can have a square wave, you have triangular or sawtooth, or a crazy wave. The wave could be looking like this and repeat. That is also a wave. And it turns out a lot of sound waves look like this, and we will see examples of that. And we will see how these weird looking waves can actually be generated by adding up a simple waves on top of each other. Very interesting. So as long as this oscillation is periodical or cyclic, then you can say that this is a wave that is propagating. And the simplest form, which I mentioned earlier, if it is in sine or cosine form, we call that a simple harmonic oscillation. So let's ask some questions now. If the frequency of a particular wave is 20 hertz, okay, so frequency now, F is equal to 20 hertz. Remember, that's 1/2. What is the period? So remember, F was equal to 1/t. Okay, so if the frequency is 20 hertz, so T would be what? 1/20 second. The vibration along a transverse wave move in a direction. Now we're talking about transverse, up and down. It's perpendicular to the wave. The distance between adjacent peak in the direction of a travel. Now, direction of a travel, okay? So we have a distance. What is it called? We already said that. So if you're looking at, this is the x-axis. So The distance would be the wavelength. The wavelength of longitudinal wave is the distance between, so it could be successive compression or successive rarefaction. When you have a wave and this wave interact with different objects, for example, I talked about oscillating your finger on the surface of the pool. The waves start propagating in a circular form and hit the edge of the pool. When they hit the edge of the pool, they reflect, bounce back, okay, from a given boundary. Depends on that boundary. Now, if you have the wave that is going from one media to another, say air into the water, what happens? Well, wave in the air has certain speed. Remember, we said V is equal to lambda times F. It's wavelength times its frequency. Now, when it goes into a different media like water, like glass, that is different media, speed changes. When the speed changes, the direction of the wave changes, and I'll talk about that in a minute. Very important phenomena called refraction, bending. Then sometimes the wave gets absorbed. All the energy that it gets absorbed in a media. That's called absorption. Another time the wave goes from one media to another media and gets out. For example, here's media 1 and here's media 2, okay, and was back to media 1. So the wave goes here and does some changes and then goes out again. Transmission. Sometimes when waves encounter an opening, okay, so we have this media and the wave goes through this, encounters opening. What happens? It can actually bend again. If you have the waves that are coming through here, it can kind of bend at the corners, or if you have a sharp edges. Now, if this opening is comparable to the wavelength wave, whatever wave that is, water wave, sound wave, light wave, okay, they can diffract. It's called diffraction. It's different than refraction. So keep these definitions in mind, and we'll talk about each example. In this course, we just concentrate on reflection and refraction. Now we have the wave that is encountering another media and the boundary. Depending on the nature of that boundary, the properties of that boundary, it behaves differently. Examples for reflection. When we have a sound wave in particular, when sound wave hits a surface, a boundary, it bounces back. And if bounces back many times, then you have a kind of an echo. By just mere reflection from a surface, you can get some interesting information about, for example, how far that surface is from you. Because if you know how fast the sound travels, by the time the sound hits that boundary and comes back to you, if you can time it, then you know how far away it is. And in fact, some animals do that all the time. So bats sense sound waves, and from the reflection from the objects nearby, they know how far and where that object is located. And ships do that all the time by sending ultrasonic waves into the ocean, and from the reflection that they get back, they know if there is another submarine there, or is at the bottom of the ocean, or what have you. The other phenomena is refraction. The wave is going through one media to another and it's bending. If you look at a wave that hits a surface of the water, for example, from air to water, it bends because it goes slower in the water than in the air. That bending depends on the property of that media, in this case is water. Or if you have a media or air that in part of the air is hotter than another layer of the air. On the hot summer day, the ground is hot. Near the ground, we have a layer of hot air. Above that, we have a colder air. If you generate a sound wave, the sound wave basically bends, going from the cold to the hot, and then bends again, going from hot to the cold. This phenomenon is called a refraction. Now, why is that? Because the speed of the propagation of the wave is changing. Let's look at an analogy to this. What happens in this case is that suppose you have a lawnmower and you push your lawnmower in the sidewalk, which is, say, smooth and concrete, into the grass. Now, the wheels on the concrete, they don't feel as much friction, so they just move nice and smooth. But let's say you have a lawnmower that the front wheels and the back wheels can actually change their direction with respect to each other. So if you enter the first two wheels, the front wheels, into the grass, but the rear wheels are still in the concrete, what happens, the ones that are in the grass, they go slower, and it causes the wheels to bend a little bit because they go slower. Because when this wheel enters, the first one enters the grass in some angle, that starts going slower, whereas the other one is still going faster, so it causes to bend. And then when the other one enters, that same thing happens. This phenomena happens where you have, for example, a light wave. We'll talk about that in very detail later on. Light wave is electromagnetic wave. It goes with certain velocity in air, but when it enters the water, it goes slower and it bends. You've noticed if you put a long stick into the water in the pool, the image that you see seems to bend it in the water. And that's the phenomenon of refraction. It's caused by change in the speed of the wave. Very important point. Then we have the interaction of wave with each other. So two or more waves can interact with each other. Well, how do they do that? Because each wave has amplitude, A. And then there's another wave here, and that has an amplitude too. Let's call that B. If they interact with each other, they encounter, their amplitude add up on top of each other. However, you know that this is plus A and this is minus A. This is plus B and this is minus B, because the wave oscillates up and down through its equilibrium position. If the waves are such that they're not propagating at the same phase, what we call it, in other words, their maxima and minimas do not coincide, they can cancel each other. This phenomenon is called superposition. Displacement of amplitude superimpose on top of each other, and then depending on where those points are, they either amplify or add up or they subtract. So let's look at an example here. So here I have two waves that approach each other. In this case, it's a pulse. It's one oscillation. We call that a pulse. But it can happen for the repetitive oscillation, as you will see in a minute. So let's run this and see what happens to these waves. Notice that as they pass each other, as you can see red and blue, at some point they add up to a very high or twice as amplitude. So let me slow down the animation. So I'm going to slow this down and see how they add up. You see, they add up, and when they both coincide, we have a very high amplitude. And then, they pass each other out. Now this is a pulse, but we can see the same thing happening when we have repetitive wave oscillating. When these amplitude add up to a higher value, we call that constructive interference. However, if they are positioned so that the maximum of one wave coincide with the minimum of the other wave, we call it out of phase, they're out of phase, then you get nothing. The whole thing cancels out. And that's called destructive. Let me show you in that animation here. We have two waves. Now these two waves, as you can see, the maximas are coinciding, they're both propagating. So as a result, you get a wave that is twice as amplitude and with same frequency or wavelength. If I put them on top of each other, they just light on top of each other, adding together. So I'm gonna move one little bit away. So the maximum of this wave doesn't coincide with the maximum. However, you still get a wave like that. So if I continue doing that, moving the phase, as you can see, the result, it's getting smaller and smaller until I have the maximum of one coincide with the minimum of the other, and that way I get nothing, flat. So if I put the two waves like that, you can see that they cancel each other out. And this is a very important phenomenon. It's called destructive interference. We have a good example for that. Some of you may have this noise cancelling headphones. There's white noise around us, noise from the car or highways. The waveform of these noises are very complicated form. Your headphone takes that, recognizes the waveform of that, and it flips it. It flips it so you get something that is complementing the other one, as you can see here. This is a better drawing than mine. It adds them both together. Because the maxima of this coincide with the minima of the other one, at every point you get nothing. So you get a nice quiet background noise. In the airplane, for example, you use that, noise cancelling. Here, almost nothing. So that's a good application for destructive interference. Here we have a water wave, two oscillating object basically touching the surface of the water, and the water is propagating and forming a very nice pattern. And that's called the interference pattern. Let's look at this. Let me play this. As you can see, each one produces a wave like that. And these waves interact. The places that the maximas coincide, you get a very large amplitude. The places that the maxima coincide with the minima of the other one, you get nothing. Can be actually shown as a pattern on a screen. And the way to do this is like this animation here. As the water drips on the surface of this pool, you can see the propagation of the waves. So these are the high or maxima, so these are the minimas. So now I open up the other one and they start interfering with each other. I have a sensor here that I can put it somewhere here at this position, but it's almost flat. I can put my other sensor here, and you can see that this is oscillating nicely, twice as amplitude. Here you have constructive interference, here you have destructive interference. You can use sound waves, does the same thing. If you have two speakers that they put the same frequency, move around in front of them, in some location you don't hear anything, but in other location you hear a sound amplified. So here you have constructive interference. Yeah. Now if you go the other side, you also have destructive interference on the other side. So there's a pattern here, and you can have a light source. So the amplitude, if you look at the result on this side or on this screen, you're going to see a pattern of bright and dim light in this case, because this is light, and that is called the interference pattern. Here's the picture of when you have, for example, a light coming from two openings. They interfere with each other, and then you see the maximas and minimas on the screen. Another phenomena is when you have source of a wave that generates a frequency, but these two frequencies are not quite the same. One is a little bit different than the other one, not much. In that case, hear or see a very interesting phenomena. It's called the beat frequency. I have a very nice video demonstration of that. I'll show you in a minute. So what happens, because the frequency of the first source is very close to frequency of second source, there's a little bit of offset. The phase is different. You see that the frequency that you hear as a result of these two, superposition of these two on top of each other, it's quite different than each one of them. And that's called beat frequency. And a good application of this is when you try to tune your instrument against a known frequency, which is the reference frequency. Tuning fork, for example, your piano. You use the tuning fork, which we know that has a very fixed frequency, and then we change the tension of the string on the piano or on a guitar or any string instrument, so that we get the same frequency coming out. Now if you're a little bit off, you can hear that beat frequency nicely, and then you know that it's not tuned. For those of you who play instruments or familiar with tuning an instrument, your ear would detect that very quickly. So let me show you this very nice video, and let me play that.
Good morning, I'm Bo. This is my presentation on beat frequency for It's probably best to start by hearing what beat frequency is. So let's start with just a 440 hertz tone. And then a 441 hertz tone. And then let's play those two frequencies together. What you hear is called the beat frequency. The equation for the beat frequency is the absolute value of the difference between the two frequencies, which is why this beat frequency is 1 hertz, or 1 cycle every second, and this beat frequency is 2 hertz, or 2 cycles every second. And then 3 hertz, and so on. Now that you know what beat frequencies sound like, let's make sure you know why beat frequencies happen. When two sinusoidal frequencies are close to one another in frequency, their two wave patterns look like this. Actually, let's overlap the two waves to better understand how the wave interference works. Hopefully you can see that the two waves alternate between being in phase and therefore constructively interfering with one another to create a larger amplitude, and then being out of phase and therefore destructively interfering with one another to create a smaller amplitude. When this happens, the amplitude of the two combined waves increases and decreases at the beat frequency, and that is why you hear beats. We can go back to the original example I had you listen to and show you the waveform for one beat. You can see the waveform for one beat has the same shape as the black wave, which is the superposition of the two waves close to one another in frequency. Again, because both waveforms show beat frequency. The top wave is the audio recording of beats, and the bottom wave is an ideal representation. A practical application of this is that beats are a useful way to tune some musical instruments. For example, on a guitar, the fourth harmonic of the low E string is at the same frequency as the third harmonic of the A string. So this is the E string, and this is the first harmonic on the E string. This is the second harmonic on the low E string. And just so you know, I am holding my finger gently on the string and not pushing down to create a node at this point and to force a harmonic at this point. So this is the second harmonic, the third harmonic, and the fourth harmonic on the low E string. And this is the A string, so this is the first harmonic on the A string, this is the second harmonic on the A string, and the third harmonic on the A string.
Okay, so you can watch the rest of this on your own if you're interested in tuning instrument. The frequency of the beat frequency is simply the subtraction of the frequencies of the two frequencies that are interacting. Another very important concept and phenomenon is called the standing wave. Say I have a wave that is propagating on this direction, hits a boundary, and then it reflects on itself. The two waves that interfering from opposite direction under certain condition, that condition is very important, they form a standing wave. Now you can try this at home. Just take a long piece of rope, tie it to the doorknob, pull it tight, not too tight, but just a little bit hanging there, and then start oscillating it up and down. Try to change the oscillation. At one point you get a feel for that. You see that the rope oscillating very nicely in certain area it doesn't oscillate at all. You feel that by changing the oscillation on your hand and noticing that phenomena. That's called a standing wave, because as a result of a wave that you send through that rope to the doorknob and the wave that gets reflected, inverted, comes back, those two interfere and they form what we call the standing wave. Let me see if I have the animation for that. Yes, I do. So here you go. You have a rope here. You tie it and then you move it. Shows what we call it the standing wave for the fundamental frequency. Then you go faster until you get to a point that you have two antinode and one not moving point of that rope, which we call it the node at the center. So here you have a fixed point that at the door or knob. Here another fixed point at your hand, and there's another one which we call it the node at the middle. Up here we have 1 and 2. Here you have 1, 2, 3 nodes and 2 antinodes. Then you start going oscillating faster until you get 1, 2, 3 antinodes, and then 1, 2, 3, 4 nodes. We can find a relationship between the wavelength of the wave oscillation and the length of the rope. And that's important because only this standing wave happen when the wavelength, in this case, is equal to 2 times the length of the rope. Okay, for n is equal to 1, so wavelength is equal to 2 times L. So let's put n here for n is equal to 1. For n is equal to 2, wavelength is equal to L. As you can see, this is one complete wavelength. This is half of the wavelength. This one is 1 and half. So for the 3, lambda is equal to 2L divided by 3. Here it was 2L divided by 2, which is L. Okay? And so on. Fundamental, this is first, second, third harmonic standing waves. So let's look at a demonstration of a standing wave. I'm gonna just start with showing, let's just take this out, and then let's look at just the string. If you oscillate this in a form that the wavelength, or in this case we said frequency, if you have the frequency, you can write that in terms of the frequency. If you have a right frequency oscillation here, you can form a standing wave. This is called a standing wave. A standing wave is oscillating in place. So this is the first harmonic. So the second one is like that, which is one complete wavelength. The third one, it's like that, and so on. You can go on for many, many harmonics. Now, if you have a pipe and a sound wave, let's look at the open-ended. So there's a pipe, just a pipe, open end, both sides, and then you start putting some frequencies, and then at some point it starts oscillating. Then if you increase that frequency, you get second harmonic, and you can see those compression and rarefactions. If you have 3, you can see that you have compressions and rarefaction. These compression points are nodes, correspond to these compressions points, just like you have in this case for the third harmonic. Now, if you have a closed end, so one side is closed. Some instruments you have a closed end and then you have an open end. And then you have first harmonic, which is a node here, an anti-node there. And then you have the third harmonic. So you have one node here, one node there, and one anti-node at this point and one anti-node at the open end. And then the fifth harmonic, one anti-node here, one node here, anti-node, node, and anti-node. Standing waves, they all happen in all the musical instruments. So the relationship between the length and wavelength of the wave is important. It has to satisfy this relationship in order for a standing wave to happen. So this is a very important relationship that you need to keep in mind, and the corresponding frequency is this relationship for different harmonics. Now, a standing wave can happen in many different media or situations. Suppose you have a ring here and you start oscillating that ring. It turns out that it sets up a standing wave if the frequency of oscillation is a multiple integer of the circumference, which is the length of this string that is closed on itself. Or it could be a surface, or it could be in some three-dimensional object, or it could be particles in a cloud. And this is what we come out when we talk about modern model of atomic structure, how the electrons are actually forming a wave, a standing wave, around the nucleus of atom. We'll discuss that in much more detail. But for now, let's look at this animation. Take a look at this demonstration. This is a string that is connected to an oscillator, and let's see how those standing waves happens.
This is a demonstration of patterns or normal modes of vibration. In this case, for a loop of wire. This is just a thin wire that is attached to a vibration generator. So at this point here, the wire is going to be moving up and down, and I have a vibration that's controlled by the signal generator that I'll be able to adjust the frequency in order to try and elicit the normal modes of vibration. With each normal mode, there's a pattern of vibration. The wire will vibrate in a number of segments. The first one I'll show you is 5 segments. And then there's a frequency associated with each normal mode as well. So each normal mode has a pattern and a frequency. So let's turn the lights out and see if we can see some patterns. Got a cool black light here for effect. So there's the 5 segment pattern, 1, 2, 3, 4, 5. If I increase the frequency,
notice before this, as he's increasing the frequency, he doesn't see a standing wave. Until it hits the right frequency, the standing wave forms.
There's a pattern with one, 2, 3, 4, 5, 6, 7 segments. I think I must have missed the one with 6 segments.
Increasing frequency, nothing, no standing wave, until the right frequency, there.
There's one of the very large number of segments in it. There's another mode with an even larger number. The higher the frequency, the larger the number of segments that it vibrates in. So that's standing waves on a circular wire loop.
Okay, now you begin to see that this phenomenon of a standing wave, and a very interesting and important phenomena. It will come back, and we will discuss this when we talk about the atomic structure, the quantum model of atomic structure. Okay, so let's go back and talk about sound waves now. Now that we learn about the properties of waves and so on, let's concentrate on the properties of sound waves. So as we mentioned earlier, sound waves are longitudinal waves, and they need a media to propagate. How does the sound wave propagate? Well, it starts to oscillate the molecule and the atoms of the media that is propagating through. If it is air, it's going to be the molecules and atoms in the air. Just as if you look at your speaker, if you crank the volume up, if your speaker surface is visible, you see the cone of your speaker, especially when you play a loud bass, starts moving back and forth, because there's a magnet back there and that's oscillating, and then it oscillating the cone, and that oscillation of the cone of the speaker oscillates the air molecules next to it, and the air molecules near that surface of that cone, they're going to start oscillating the next neighboring molecules, and the next neighboring molecules is going to oscillate the next neighboring, and so on, until that oscillation, as you saw the animation, in the form of a longitudinal wave, and until it hits your eardrum. When it hits your eardrum, that energy has been transferred from the cone of your speaker into your ear. Your eardrum interprets that as a sound that you hear. Now here we have a table that tells you how fast sound travels in different media. Well, contrary to some common belief, sound travels a lot faster in solid than liquid than gas. And the reason for that is this: the atoms and molecules in solid are next to each other, and they can actually very quickly transfer this energy from one molecule to another. If you notice some of the old the cowboy movies, they wanted to rob a train that is coming from far distance, they would put their ear on the railroad, and they would hear the sound of the train coming from far distance, because the sound that the train generates on the railroad would propagate much faster than the sound that it comes through the air. In a steel, it goes at almost 6,000 meters per second. Aluminum is 64,000 almost. Let's say just seawater, for example. It's almost 1,500 meters per second. In air, it's about 340 meters per second. Of course, depends on the temperature of the air as well, as we'll see that in a minute. And as I mentioned, the source generates a sound and it hits your ear by just oscillation of air molecules. And of course, an eardrum vibrates, and that vibration is transferred to some of these nerves here, and the nerves transfer that to your brain, and you recognize that as a sound. Frequencies that we can hear is limited. It only from 20 hertz to 20,000 hertz or 20 kilohertz. Below that, we have infrasonic, which we don't hear it. This is when you have your bass. Musical bass is a little bit higher than that, but you can feel it. Have you noticed that someone in the car playing a very loud sound, you only hear the bass, boom, boom, boom. Lower frequency actually penetrate much easier through, and you can actually hear it. Sometimes in movies, when they play a huge bass sound effect, you can feel a little bit of a vibration there. On the other side, 20 kilohertz, okay, so we don't hear beyond that. The normal ear can hear between 20 to 20 kilohertz, 20 hertz to 20 kilohertz. But as you grow older, that range narrows down. So you lose hearing at the higher as well as lower sound spectrum. Some animals can hear ultrasonic much better, and dolphins, for example, dogs and other animals can hear that. And of course, it has a lot of good application, like ultrasound. Ultrasound, you send a ultrasound signal into the body, and the reflection from that is received by the receiver and interprets as an image of the layers of organs that you're actually monitoring. Ultrasound is very important and has a very good application, and it's much better than X-ray, because X-ray can actually damage some of the cells in your body. Too much of an exposure of X-ray can actually be harmful, whereas ultrasound is not harmful. They use ultrasound for other application, like cleaning your teeth. You have ultrasound that breaks the plaques in your teeth, tuning forks that provide you a fixed frequency for each fundamental frequencies that we use in the musical instruments. And these tuning forks, as you can notice, and this one is 512, that represents the note C. And then you have others, depending on the length of that, as you hit the tuning fork, you actually get a different frequency. Sound also can have a large amplitude, which would be high intensity. The intensity is defined as the amount of power of sound that goes through an area. Now, the area of your ear is probably 1 centimeter or less squared. The amount of power, remember, power was what? Energy per time. Okay? Now, power per area is called intensity. So you can say that intensity is equal to energy per area, time per area. So intensity is rate of energy transfer through an area. And we use that to find out how loud or how low is the sound, okay? And relates to the amplitude of the sound. So if you have a sound wave that is like this, the amplitude squared, that proportional to the intensity. The unit of the intensity, because power unit is watt and area is meter squared, so that would be the unit of intensity. So now let's look at how that relates to loudness. Well, loudness is relative. Something that is loud for you may not be loud for me. Loudness is subjective. So we really don't use that. We use the intensity. We measure the sound intensity, and we see that the normal ear can distinguish the intensity from very, very, very faint sound, which is 10 to the minus 12 watt per meter square, all the way to 1 watt per meter square. So that's the range that normal, human hearing can detect. Now, of course, here we have a huge amount of power, and you can actually start hurting your eardrum when you're, getting at the higher end. Let's look at the range here. Threshold or lowest faint whisper that you hear is 10 to the minus 12 watt per meter square. And the high one, which is really loud, that's 1 watt per meter square. Now, you don't want to be exposed to that kind of a intensity because it can hurt your eardrum. Have you noticed that if you've gone to these loud concert, and if you're close to that, speakers in front of the stage, after an hour or two, when you come out, how does your ear feels? It feels muffled. You cannot hear certain things after that for a while, because your eardrum has gone crazy, stretched back and forth, oscillated back and forth at that loud noise. That's why the air traffic guys in the tarmac, they wear these muffled so that they don't damage their ear, because the jet aircraft engine is very loud. Now, rather than writing intensity in terms of read 10 to the minus, say, 8 watt per meter square, it's easier to use, because there's a power of 10. In mathematics, you can represent this power of 10 in terms of logarithmic scale or decibel. What does that mean? That means if you have 10 to the minus 12, which is the lowest intensity you can hear assigned to what we call the 0 dB, decibel, 10 to the minus 12. Then the highest one would be 120 decibel. That represents 1 watt per meter square. And then anything in between are represented by this decibel. That's why your audio knobs are marked as dB, decibels, to represent how much power, how much intensity is being put out by your stereo system. So if you look at the range, we have the scale in terms of a decibel. 0 is threshold of hearing, and then you go just if you have a regular conversation. So we are actually doing around 60 decibel when I'm just having conversation and talking with you guys. And then the traffic out there is 70, higher. Rock concert 110. Okay, the jet engine is actually all the way up to 140. They launch a rocket is 180. Whew. You don't want to be near that. It can actually puncture or break your eardrum. If you look at a decibel range, you can see that the comfortable level is in terms of a decibel, it goes to about 60, 70 from 30 to 60 in this range, and the frequencies covered from 200 hertz to about 5,000 or 5 kilohertz. When you play music, depending how loud it is, you can go as high as 100. In rock concert is 110, down to about 30 dB, and on this end you can go up to about 10 or 15 kilohertz, and then on the lower end is about 50 hertz, and then anything above here, it is going to be painful. So this tells you what is the range that we can tolerate. So remember the parameters that describe the waves: the speed, the wavelength, period, and frequencies. Okay, so and the relationship between them. All of that applies to sound wave as well. Looking at speed of sound in air, we can measure that. It's measured to be 344 meter per second, 20 degrees C. 25 degrees C is room temperature. So it's a little bit colder than room temperature. At 0 degrees C, it goes at 331 meter per second. Of course, we saw that our speed of sound increases as the density of material increases. If you know speed of sound at 0 degree, okay, you can find the speed of at any temperature. It's equal to 331 meter per second plus, now is a factor, just a factor, which is 0.6 meter per second per degree C times the temperature. So that's the relationship that gives you the speed of sound depending on the temperature of the medium. So in air, we already said that is 344, at 0 degrees 331, at minus 20 degrees C it's slower. In glass is high, steel is high, water is lower than steel, and wood is higher than water. So you can see how the speed of sound changes in different media. Now, of course, the speed of light is way faster than the speed of sound. So that's 310 to the 8 meter per second. So if something happens in a distance, we can see that much quicker than we can hear it. So that's because sound travels slower, much slower than the light. Light, we can immediately see it, almost immediately. So speed of sound is, as we said, around 331 at 0 degree. And that's roughly 5 miles a second. If you hear the thunder and you see the lightning right away, but you hear the thunder a little bit later, every second is 5 miles away. So if you count 4 seconds, so 4 times 5, that means 20 miles away. So question for you. You watch the person chopping wood. You see that right away. You hear it 1 second later. So how far is the chopper away? And that's about 5 miles away. So you hear thunder 3 seconds after you see the lightning. How far away is the lightning? Or 3 times 330, it's more than 660. A wave with wavelength of 10 meter and time between the crest, half a second, is traveling in water. What is the wave speed? The relationship for wave speed was equal to lambda, wavelength, times the frequency. And that was equal to lambda divided by the period. Wavelength is 10 meter. So lambda is 10 meter. Time between crest, period is 0.5. So 10 divided by 0.5 is 20 meter per second. What is the lambda of a sound wave in air at 20 degrees C with a frequency of 22 megahertz? So what do we have here? We have the frequency 22 megahertz. That means 22 million hertz. 22 times 10 to the 6 hertz. So we have to convert that. And we know at 20 degrees C, we just saw that the speed of sound is 344 meter per second. What is the wavelength? We want to find wavelength. Relationship between wavelength, frequency, and velocity, we use that. Lambda is equal to V over F. So 344 meter per second divided by 2210 to the 6 hertz, and that's 1610 to the minus 6 meter. So that's the wavelength of that sound wave. Now, suppose you have a source of sound, and now you move away or you move towards it, or the sound wave moves towards you or away from you. You hear a different pitch, although that source is providing the same frequency, but what you hear is different. This is called Doppler effect, and very important effect. Now you may have noticed this, a siren, a police car coming behind you and then speeding and passing away from you. You hear different pitch as it comes behind you, and then as it moves away from you. You hear a higher pitch when it comes towards you. You hear a lower pitch when it goes away from you. So if we can measure that pitch, which we can with some instruments, then we know how fast that is approaching us or how fast it's receding from us. So Doppler effect is apparent change in frequency that you hear. Or in case of a light, you see, because that applies to the light as well. So let's look at this animation.
Good morning. The Doppler effect is named after Christian Doppler, a 19th century mathematician and physicist who was able to mathematically describe what is now called the Doppler effect. And it sounds like this.
Perhaps you are already familiar with how the Doppler effect sounds. However, I'm here to make sure you understand why it sounds this way.
Oh, great. I always want to know why.
Me too. Actually, you know what? I do too.
Alright, so it starts by recalling what this animation of a stationary sound source actually represents. So, Bobby, remind me, please. Actually, rather than using the car horn, let's switch to a constant 440 Hz frequency being played on the speakers of the car stereo. That is the 440 hertz concert pitch, which we used last time.
It's harder to hear the Doppler effect at 440 hertz rather than the car horn. Can we just stick with the car horn?
Okay, we can go back to the car horn. However, the Doppler effect is easier to understand if we refer to a single frequency. So let's keep referring to the demonstration as a single frequency, but use the car horn demonstration. Sorry, Bobby. We're back to you. You are telling us what this animation of a stationary sound source actually represents.
Right. Remember, sound is a longitudinal pressure wave,
And those lines are crests.
which are also called wave fronts.
Yeah, thanks. So sound is periodic changes in pressure in the medium, which in this case is air. Each of those lines represents a crest in the longitudinal pressure wave. That means each crest or wavefront is a location of high pressure. That periodic pressure wave transfers sound energy through the air. And the reason all those circles are the same distance from one another is because the sound source is oscillating in simple harmonic motion at a constant frequency.
Do not forget that each circle actually represents a spherical pressure wave or wavefront going out in all directions from the sound source. It is a circle instead of a sphere here because this is a two-dimensional space.
Very nice, everybody. Now remember, this animation is for a stationary sound source. Look at how the animation changes when the source of the sound is moving.
Huh, I like that.
Good, but I want to make sure that you are aware that each of those circles, which are actually spheres, represent the sound coming from where the sound source was when it emitted the sound. To make that clear, I have highlighted one of the wave crests so you can see that it is a sphere that is increasing in size, and the center of that sphere continues to be in the location where the car was when the sound was emitted by the speakers of the car. Sometimes that is a concept which gets lost in the overall understanding of this.
Okay,
Thanks.
got it.
Okay.
Now let's add a human to our animation. Notice the human, or the observer, is currently located such that the car, the source of the sound, is coming towards the observer. Bo, what do you notice about the distance between the spheres that are going towards the observer?
On the side of the car where the guy is, the circles are closer to one another.
And what does that mean?
Well, the circles represent crests in the wave, and the distance between two crests of a wave is the wavelength of the wave. I guess that means that the wavelength of the sound wave which the guy hears when the car is moving toward him is less than the wavelength of the original sound.
Correct, Bo. The wavelength of the sound heard by the observer when the sound source is moving toward them is smaller than the wavelength of the original sound. And Billy, what does that mean for the frequency of the sound heard by the observer in this example?
Okay, the observed wavelength is decreased, and you are asking how that affects the observed frequency. Well, we know the speed of a wave equals the frequency of a wave times its wavelength. That means the frequency and wavelength of a wave are inversely related. That means if the observed wavelength is decreased, the observed frequency must be increased. In other words, when a sound source is moving towards an observer, the sound heard by the observer has a smaller wavelength and larger frequency. A larger frequency sounds like a higher pitch to us, so the sound we hear when the car is coming towards us has a higher pitch.
Absolutely correct, Billy. Bobby, could you please talk about what happens when the car is moving away from the observer?
Okay, this should be the inverse of what we just talked about. Now the crests are farther away from one another, so the wavelength of the observed wave is larger. Wavelength and frequency are inversely related to one another, so because the observed wavelength is increased, the observed frequency is decreased. That is why the frequency and pitch of the observed sound are lower when the car is moving away from us.
Very nice, Bobby, but I want to specify that the frequency and wavelength of the sound source remain unchanged. To reiterate that point, please enjoy this split screen of two different viewpoints during the demonstration.
On the left, you see me in the car, and on the right, you see the event from the perspective of the stationary observer. Before we heard what was happening from the perspective of the stationary observer. Now let's listen to what we hear from inside the car. The frequency and therefore the pitch you hear is constant.
Sure, the person who is in the car is not moving relative to the source of the sound, so the wavelength and frequency they observe are not affected by the motion of the car. Thanks.
But what if it's reversed and the car is stationary and the person is moving?
Great question, Bobby. That actually causes the same Doppler effect. If the sound source is stationary and the observer is moving, as the observer moves toward the stationary sound source, the observed wavelength is still decreased, and therefore the observed frequency is still increased. And the reverse is true as the observer moves away from the stationary sound source.
Excellent. One of the things that we use Doppler effect is to find out what is happening to the distant stars or galaxies, and what's happening in general with the situation of the universe and how these galaxies are moving with respect to us. Stars are usually formed in a binary fashion. They kind of rotate around each other with respect to the center of mass of both. And then we can actually observe that rotation and find out what's happening there by just looking at their Doppler effect. As they rotate, one is actually getting closer to us and the other one is getting further away from us, and this tells us that one of them's frequency is higher and the other one is lower. So we know that the higher frequency is towards a blue light and lower frequency is towards the red. That gives us a clue or indication that one of them is receding from us, the other one is approaching from us, and this thing's kind of continues, and that tells us that here is a binary star that is rotating around the center of mass. When we look at the sky, and we especially with the Hubble telescope, we have noticed that almost all the galaxies and stars and everything else is actually receding from us just by observing the light frequency shift that they send us, and this is called the redshift effect. Now there are some stars or local galaxies shows the blue shift, which means they're coming towards us. By using this Doppler phenomena, we are able to say that entire universe are actually moving away and expanding. And this is the phenomena that led us to believe that at some point all the matter were condensed, and as a result of an explosion, which we call the Big Bang, started to propagate and expand throughout the space. And now we are at this point observing that this expansion is happening, and that's what we have the theory of a Big Bang. Another phenomenon that happens when we're looking at the sound wave, what happens if there was a very high-speed jet airplane that moves much faster than 334 meters per second, and we do have such jets that they can go twice or three times of the sound waves. If we look at the waves that are propagated from the source of this the moving object, in this case you have, say, the airplane is moving not as fast as sound wave, So you also have the Doppler effect, and you see as towards the motion of this airplane, the wave fronts are getting closer to each other, and the frequency is higher. As you approach to this speed of sound, which is around, say, 344 meters per second, then you can actually generate the sound, and they bunch up on the wave fronts, because now you're going at the same speed of sound, right? So you have a lot of amplitude. These lines represents the amplitude of the sound. A lot of these are now bunched up on top of each other, so you get a larger and larger amplitude. And then if you pass that, say your airplane or jet engine is going faster, twice as big of a speed of sound, then as you generate the sound, wave fronts are adding on top of each other, and they form a cone that all the amplitude around this cone generate a huge sound. And that's what we call the shock wave. Actually, visibly, you can see the air molecules that are experiencing that kind of a vibration of shock waves can be visibly noticed. And on the ground, you hear a huge sonic boom. Another phenomenon that is extremely important, considering the sound and waves in general, it's that every object that you can imagine has some sort of what we call it a natural frequency. That natural frequency, it's a property of that object, no matter what it is, in what shape. And if you somehow generate externally a frequency that is matching natural frequency of that object, then you start to stimulate that natural frequency starts to oscillate on that object. You need some sort of an external stimuli so that you can kind of vibrate the media and transmit that vibration into that object, and that object now has the same natural frequency as your stimuli, then that's going to start oscillate as well. And a good example of that is when you're looking at a wine glass and you start a sound wave externally and you change the frequency until it matches this natural frequency of the glass. And at that point you see it will break. So let's watch this. So that's about the natural frequency of that glass. So if you have an external sound generator with close to that frequency, let's see what happens. So he's changing the frequency to get close to that. A slow motion, you can see it starts oscillating. As you saw, the outside external, or we call it the force vibration from external source, it started to stimulate the natural frequency of the wine glass, and it broke. Now in musical instrument, we take advantage of this, and we built a cavity that when you have, for example, a string tied to fixed point and you plunk on it and it starts vibrating, you don't hear much. But if you have it next to a cavity that cavity has a natural frequency close to the frequency of that string, then you can hear it very nicely, okay? And that's what we get as nice loud sound from a musical instrument like the guitar or violin and so on. Another example of natural frequency is when a resonance is when you start, for example, swinging a mass.
Good morning. Flippin' physics. Resonance involves standing wave patterns. So if you have not learned about standing waves, please enjoy my video about standing wave patterns. Link is in the description. Here we go. As I slide my fingers across this aluminum rod, the friction between my hand and the rod causes vibrations which set up a standing wave pattern in the rod because the rod has a resonance frequency and resonance wavelength determined by the physical characteristics of the rod. Because I am holding the rod in the center of the rod, that forces the center of the rod to not vibrate. Bo, in terms of nodes and antinodes, what do you think that means for the movement of the rod?
Okay, the location you hold the rod at forces the rod to not vibrate there, so that must be a node. I'm guessing then that the two ends of the rod probably vibrate the most, which would make the two ends antinodes.
Correct. So you can hear that standing waves are happening in this rod. In other words, this rod is resonating, which is why this frequency you hear is called the resonance frequency of the rod. Another term often used is that this is the natural frequency of the rod. In other words, the friction between my fingers and the rod oscillate the rod at the resonance frequency of the rod, causing standing wave patterns in the rod, which is called resonance.
I'm sorry, what?
Yeah, I don't get it. Okay, let's switch to a simpler example. This is a swing, which is a pendulum. A pendulum has a natural frequency at which it oscillates. If I apply a force to the pendulum at a frequency which matches the natural or resonance frequency of the pendulum, the amplitude of the pendulum will increase. The pendulum will be resonating due to my force applied at the natural frequency of the pendulum. If instead I apply a force to the pendulum which is at a frequency which does not match the natural frequency of the pendulum, the amplitude of the pendulum will not increase.
Sure. Applying a force at a frequency which closely matches the resonance frequency of the object will set up standing wave patterns in the object, which is called resonance.
Correct, Billy. We can do the same thing we did with the aluminum rod with a goblet. By running my damp finger over the top of this goblet, I set up a standing wave pattern in the goblet at its resonance frequency, which you can clearly hear. When I change the amount of water in the goblet, I can change the natural or resonance frequency of the goblet. You can even see that the vibrations of the goblet cause ripples in the water. A hollow tube has air in it, which will also resonate at particular frequencies, which is why if I hold an oscillating tuning fork over a hollow tube with one end in water, I can adjust the length of the hollow tube, which is filled with air, therefore changing the resonance frequency of the air column inside the tube until it matches the frequency of the tuning fork. And when the frequency of the tuning fork matches the resonance frequency of the air column inside the hollow tube, you can hear the louder standing wave pattern which has been established in the air column inside the hollow tube. When I change the frequency of the tuning fork, you can see it changes the length of the tube, which is out of the water in which the standing wave pattern is created, and therefore changes the resonance frequency of the air column in the hollow tube.
Okay, so you can watch the rest of this, which is very interesting, on your own, and let's continue our discussion. When we have resonance, sometimes this forced vibration or natural frequency has to be avoided because it can be devastating. For example, if you're architect, engineer, and you are designing a high-rise, especially our area because we have a lot of earthquake, what you need to do is you need to design your high-rise so its natural frequency it's way away from the normal frequency of the earthquake that happened around us. Because whenever an earthquake happens, we know based on our data and so on what are the range of frequencies. Of course, the amplitude changes, depending on the Richter scale and so on. But if we kind of know what the range of frequencies of earthquake we should avoid, then when earthquake happens, we will not have a resonance or increase in oscillation of those high rises, which could practically collapse it. It's important to design those high rises so the natural frequency of those high rises, of course there's a lot of complicated factors that you have to take in your design to avoid the frequency range of the earthquake that happens in our area. In fact, one of the devastating phenomena that happened back in 1940 was Tacoma Bridge collapse. I'm not sure if some of you have seen this or not, but this is actually a bridge, a suspended bridge, as a result of the air movement through that bridge. What happened, it started to oscillate, and someone had this is actual footage of that problem. Someone was able to take a video of that in a slow motion, showing that the bridge, the road on the bridge is actually oscillating because of the motion of the air going through, oscillation of the external forced oscillation causing this to resonance. And then if that gets higher and higher amplitude, eventually the bridge actually collapses. So I'm just going to fast forward. You can watch this in the interest of time. You can see how that bridge is oscillating until it actually collapses. You can see the collapse of the So when we're looking at the resonance in musical instrument, we obviously have a regular and controlled vibration that kind of gives us a nice musical tone. Otherwise, if you don't have that regular and controlled vibration, you will have noise. When you are looking at a musical instrument and you kind of look at the different harmonics of that musical instrument, you can see that while you're playing a note, there are many harmonics involved there, and they kind of add on top of each other to produce a sound that you hear. If you look at this animation here, for example, the first harmonic of this violin is shown here, and if you add the second harmonic, then the two harmonics, the red and green, are adding on top of each other to produce the result, which is the standing wave, white wave here, as you see. And then you can add the third harmonic and the fourth harmonic, and so on. The sound that comes out of these instruments are superposition of many harmonics, and in a very complex way, but each harmonic is basically a sinusoidal wave that kind of superimposes on top of each other and produces the sound that you hear. Let's move on. Of course, the string instruments, the sound and the frequency that's generated depends on the type of string, the material, and then the tension on the string and the length of the string. So all of those are designed with the body of the instrument. Then sound resonate in that cavity, and you can hear that very nicely. When we're looking at the musical instrument, the characteristics of the musical tone basically contains the pitch or frequency of the note, the intensity of that, how loud that is, and the quality of that. Pitch has to do with the frequency and the fundamental frequency of that note. For example, if you look at the guitar string, the first, it's an E string. That's the fundamental frequency of that. And then you can have multiple higher harmonics of that. Then the intensity of that has to do with how loud that sound coming out from the cavity of that instrument. And then quality has to do with what are the harmonics involved in that sound that is coming out and you hear. The musical pitch or frequencies are denoted by, musical note. We call them, A, B, C, D, E, F, G, and then you have half notes between some of these. And then in Europe they call it do, re, mi, fa, sol, la, si, or la, si, do, re, mi, fa, sol. It's corresponding to A, B, C, D, F, G. One octave, it's notes that starts from A and ends at G, and then repeats again. So you go to a higher octave on this side and the lower octave on the other side. So then when you have your piano notes, for example, you have a note C, say at 523.25 hertz. If you multiply that by 2, you get to the second octave, higher octave of the C. And if you multiply that by 2, you get to the higher octave, and so on. And then, if you divide that by 2, you get to the lower octave. And then if you continue, divide that by 2 and divide this by 2, you get a lower and lower pitch or octave. Now, the question may be that why is it that octaves sound the same pitch? Well, when you are hearing a note, for example, played in the piano, is really not a single frequency. If you watch that in the oscilloscope, you will see that is not a very smooth sinusoidal. Is rather some complicated waveform, and that means that it contains higher harmonics in. When you are playing in a note A, you are actually including the higher harmonics or lower harmonics than A, which is at 440 hertz. You probably have 220, and you have 880 and 1760 hertz, all added on top of each other to give you a shape of the note that is coming out, and that is the quality of the sound you hear. Now you hear the note A frequency because that's the fundamental frequency, and it has highest amplitude, and that is predominant one, and that's why you can say, even though there are harmonics there, you say that's a note A and has the highest amplitude. As you can see, the simple sine wave, it's, as we are familiar with, is like this, but when you play a note in a guitar, it looks like that. Although it has a repetitive nature, which should, but it contains few harmonics added on top of each other to get this one, or in the piano. So here's some other example. Now, if you are using a tuning fork of a fixed frequency, then you get a nice sinusoidal wave. The last thing we want to talk about in this chapter is a little bit about the different type of waves. We talked about sound waves, mechanical waves, water waves, but now we are talking about electromagnetic wave. We talked about electromagnetic wave as waves that can propagate through vacuum. They don't need any medium. They can propagate at the speed of light. And light actually is a part of electromagnetic wave. And that's why we see what's coming from stars and reflected from planets or coming from galaxies and so on. These electromagnetic waves are a form of electrical and magnetic oscillation coupled together. And we will talk about this a lot more later on. When you have an electric field and a magnetic field, they couple together, they propagate as a wave throughout the space, and they have a peculiar situation that electric field and magnetic field are perpendicular to each other, and as we will see later on, they keep regenerating each other. So when you have an electric field that is oscillating in a space, it generates a magnetic field that is oscillating. When that magnetic field is oscillating, is going to generate an electric field. And this process continues. And that's why these electromagnetic waves or light continue regenerate each other throughout the space and go forever until they actually interact with other objects or other waves. If you look at the animation of this, you will see that let's say the electric field are the ones that are represented by a green that goes up and down, and then the magnetic field are generated at the same by the process of change of electric field. Magnetic field are generated. Once the magnetic field are generated and changing, they generate electric field, and this process continues. And as a result, you have an electromagnetic wave that is moving at the speed of light. Let's look at what are the electromagnetic waves that we know. It starts from very high frequency and short wavelength, which called gamma rays. And then we move on to X-ray, less frequency than gamma ray, and lower frequency yet is ultraviolet, until we get to the visible spectrum that we are able to actually see. Visible spectrum starts from the ultraviolet frequency, goes through blue, bluish, green, yellow, orange, and basically rainbow colors, all the way to red, and then it goes to infrared. So a very small portion of this electromagnetic spectrum belongs to visible portion. And then infrared, we won't see it, but with instruments, obviously with instrument we can see everything that you see in this spectrum, from gamma ray all the way to radio wave. Your instrument is your radio, right? You can detect the radio wave and listen to, which is very long wavelength. After infrared, you have microwave, and then you have radio waves for FM, AM, which is lower frequency. FM is order of megahertz. Here is kilohertz. Then we go to long radio waves, and some of these are used in aviation. Some of these is used in broadcasting, TV or cell phones. Some of these are reserved for the police communication and so on. And the size of these are basically, when you talk about the radio waves, is huge. The wavelength could be order of 400 or 500 meter, 1,000 meter. Or when you get to microwave, are, size of the bees, and then you have infrared, and then visible, it's from 400 nanometer to 700 nanometer. And then when you get to ultraviolet and you get to size of the molecules, and then X-ray is the size of the atom. That's why we can use to kind of get some information from different materials, sort of like crystals. We can actually have diffraction patterns coming out from the crystal by shining the X-ray on it, and we can get information about the size of the atom, the spacing between the atoms in the crystal, and so on. And then we move on to the size of the nucleus, 10 to the minus 15 meter. So those are the areas that we look at the wavelength of the gamma rays, high frequency, short wavelength. Visible light, as I said, it's order of 400 nanometers to 700 nanometer. Nanometer is 10 to the minus 9 meter. And then obviously how bright it is, that has to do with its intensity and the energy that outputted by the source of the light or electromagnetic wave. So let's do an example here. We want to find out what is the wavelength of a radio wave that is produced by a station. So you tune into your radio, it says 700 kilohertz. That's the frequency of it. Oops. So you have to convert that to hertz. We know the speed of light in SI unit is 310 to the 8 meter per second, and divided by the frequency. We know the relationship between the frequency and the speed and the wavelength. So that's 428 point. The frequencies that are used to broadcast radios, FM and AM, ranges are, for AM is 800 kilohertz, and for FM is about 90 megahertz. So 10 to the 6, 90 10 to the 6, or 9 10 to the 7 hertz. In order to send information at that frequency, you kind of use what we call it the amplitude modulation. So you add an information which is a form of speech or music or what have you on top of that frequency, that you change the amplitude but keep the frequency the same. So that way you can add information and send it through a signal so that you can detect a sound or music or a speech. In the case of FM modulation or frequency modulation, you send the information, keeping the amplitude the same, just changing the frequency to broadcast different forms of speech or things. So we call it FM modulation. This concludes chapter 5, which was about wave and sound and a little bit about electromagnetic waves. So I'll see you next time. Have a great day.